So, welcome to Masterminds in Maintenance, a podcast for those with new ideas in maintenance. I'm your host. I'm Ryan. I'm the CEO and founder of UpKeep. Each week, I'll be meeting with a guest who's had an idea for how to shake things up in the maintenance and reliability industry. Sometimes the idea failed, sometimes it made their business more successful, and other times it revolutionized an entire industry. Today's guest is Fred Schenkelberg,
Yep, got
reliability. I got it. Reliability engineering and management consultant extraordinaire. Welcome, Fred, to our show.
All right, thanks, Ryan. Thanks for the invite, and congratulations on launching a podcast series. That's awesome.
Of course. And we're all extremely excited to have you on to today's show. Maybe you could start us off by sharing a little bit more about yourself and how you got started in this kind of funny industry.
Well, I have found in talking to lots and lots of people in the reliability world that my circumstance wasn't unique. My boss walked in one day. I was working in an R&D engineer at a factory where we were making cabling cable products. And he said, "We need to know if this will last for 20 years or not. Here, go figure it out." And I have no idea. I started my career there as a manufacturing engineer. And so I had the firm belief that it was always the design's fault, the design team's fault. If it doesn't work, it's a design problem. And it's hard to argue with that. Now, manufacturing can certainly make products worse. We have variability, but if you design for it, that's a good thing. So anyway, that's how I got started. My boss said, "Go figure this out." So I didn't even know what reliability was. I still don't know how to spell it 9 times out of 10. And I got thrown into the deep end of the pool and got a nice technical paper out of the study we did and learned a lot. It still gets cited, which is kind of exciting. And found that I really enjoyed the statistics and the types of questions I got to answer. And that just led to one opportunity after another. And then about 15 years ago, I went into consulting. From when I was at Hewlett-Packard, I switched to consulting. And never missed a beat. I've had a blast and worked with hundreds and hundreds of companies and all around the world. And it's been fun. And there's never a lack of things failing. So it's a never ending job.
Well, awesome. You mentioned it really started from that one paper. Could you share a little bit more about what that paper was and why it still gets cited today?
Well, we made a heating cable. I don't know if you're familiar with heat tape or heat trace. It's a cable essentially that you strap onto a pipe, for example. And let's say you're at a nursing home and you have a hot water heater in the middle of the building, but you want hot water out at the last end of the hallway, right? You want the same temperature. So you could recirculate it, but that's a pump and more pipe and it's expensive. So we put a heating cable on it that replaces the heat loss so that at the end of the line, it's the same temperature. And so we made a cable that was self-regulating. It had just enough carbon black in it that in the polymer with these 2 electrodes going right through the middle of it, that if it was cold in one spot, like if you put an ice cube on it, that 1 inch would heat up. Wow. So it was a pretty cool product. And it was just material science that allowed us to make these things. But we didn't know how they failed. We knew that they lost power, the ability to generate heat over time, but not exactly how. And if it would last 20 years, because this new product was going to be buried in concrete bridges in the Alps to melt snow. And they didn't want to tear it out and replace it every 5 years, obviously. So my boss said, "We need to know if this design will last for 20 years. And what came out of that was that it's not a straight line behavior, right? We could approximate it with that it starts at 100% power and then slowly decays. And what we've done in the past is just drew a straight line through that and said, here's the projection to when it fails. But we found in experience that those products always lasted much longer than we projected. So I did a longer test and more accurate, and we measured the curvature of that decay. Then we went into the lab and figured out that the outer surface of the polymer oxidized and created a barrier to more oxygen molecules getting deeper into the product. So it's like a oxidation that, like a tin oxide, it protects the surface from further decay. And so I worked with a professor out of Toronto that, and between the two of us, we came up with this technique to model that curvature. And so it was a degradation analysis, and it's technically called a Wiener diffusion process.
Oh.
And so we applied it to that model, and that paper on a novel way to do degradation analysis still gets cited.
Wow,
So,
that sounds, extremely complex, but it also sounds like it had a massive impact on the business that you're working for, which is
yeah, we did get the business. We did get the Italian. I never got to go to Italy to go see it installed or spend 20 years there to see if it worked, and but we did get the business. But it also dramatically changed how we tested our products and how we evaluated it and how we understood how it failed. And so then that first test took about 6 months to do all the analysis and data collection and everything else. And we shortened that after that point, because of that understanding, we could only go 2-3 months and get as good information almost. So it helped all the way around.
Wow. All right. So, I always ask this question, what does reliability really mean to you? Can you share with our audience what reliability engineering is?
Well, there's two answers to that. One of them is what it means to me, right? And I can have a short story for you for that. The second part is what we do is in reliability engineering is enable the rest of the organization to make better decisions. That's what we do, right? We help them understand what will fail and when will it fail. But realizing that as you design and create a system to maintain a product, there's a lot of decisions that are made, right? If you've got the right information and good information available to you and know how to understand it, analyze it, you will make the right decision. Do I need a calendar-based program, or do I do it by inspection, or what's the right way to set up my program? Or on the design, do I go with vendor A or vendor B, or is it ready to launch or not? Part of that decision is not just, we got to do something. Oh yeah, reliability is important, but we don't know how to include that in the decision. So what reliability engineers do is help understand what information is needed to make the right decision, and then either help or get that information to them to make that work. So that's one way I understand reliability engineering. We also get to break things, which is way cool. So it's the sort of thing I like. The other part of it is that it was a Friday afternoon. I was working at Hewlett Packard in a corporate group, and I got a phone call from the sales engineer. Now, I almost never got calls from sales engineers from our own company trying to sell me anything. But she called and said, tomorrow, Saturday morning, I have to go into one of our major clients or customers that is received the first shipment of like 7 laptops or 10 laptops, and 7 of them were broken in broken screens. They dead on arrival. And I said, well, I'm not the laptop guy, She said, well, we're working on that. But I have to go in there and explain why they should not cancel the rest of the order, right? What is it about the HP's culture and reliability attitude that's going to help us feel confident that the rest of these products are going to be good, right? And so we talked for about a half hour, going back and forth about different historical things and internal training and all the different things we do, in which I was pretty involved with across the corporation, to make sure that our reliability is built in and designed into our product, and by and large, every stage of the way. And so she was feeling good about what she was going to say, but then she stopped and said, I don't think I can do this anymore. And I went, excuse me, what do you mean? And she goes, when I go sell this product, it's based on, a large part is based on that it's reliable, that it's durable. It will do what it says it's going to do, that we assembled it correctly, we packaged it correctly, we designed it correctly, and it'll meet or beat your expectations. And that's not happening, right? This is not the only time I've been disappointed by a shipment to a customer, and I'm their face, right? I'm the face of this thing. And she says, I'm not willing to jeopardize my integrity by saying it's going to be reliable and it's not. And so I never did find out whether she stayed in the company or left or whatever, but that sums up what reliability means to me, is that
Yeah.
there's a person on the other end of our processes and our techniques and all of the work we do to get products into the market, and it's got to work. It's got to do what it's supposed to do. And if there's an error on the line, or we got a bad batch, or the worst is you let a bunch of engineers on the floor to make products, and it becomes just a bunch of experiments. At the end of the day, somebody's going to open that box and turn it on. And if it works, it's great. If it doesn't work, you've disappointed somebody with a set of expectations being dashed. And so the reliability is very, very personal, right? Every individual interaction with our products reflects on the entire organization. And so reliability is a big part of that.
Absolutely. Absolutely. I mean, it seems like, Fred, you've dedicated your entire career to reliability. It means a lot to you.
Yeah. And it pays well too. So it's not a bad deal.
And it seems like you've also, not only dedicated your career, but you've built a company based off of reliability engineering. And I got to ask the question, working as a consultant now, what's the most common reason? What's the trigger point for people to reach out to you guys and say, hey, we would love to have a reliability consultant come to us? What typically happens? What do people realize right before they realize they need to call you guys?
Well, unfortunately, about a third of my clients call when they're heading towards bankruptcy because their product's just a disaster in the field, and they go, oops, we should have paid attention to that. Yeah, and some of those companies make it and others don't. They get this, realization that they made some bad assumptions, or they, reliability is there, but it's too expensive, or it'll take too long. And so they just say, well, we'll do our best. And they don't do due diligence as a minimum. And then they get surprised that it doesn't work, right? About a third of my clients are in that boat. Wow. About a third are folks that are looking at their program, their overall system of how they make those decisions, what information they have, what tools they're using, and they recognize that they could do better. They say, we keep doing what we're doing and we keep getting this result, and we need to improve our reliability. What do we need to change, right? And so I get called in to do an assessment, essentially, and find out how an organization understands and makes decisions concerning reliability, what's working and what's not working, and so on. So about a third of my clients are at some stage in their programs, but have a realization they should be doing better. And so it's not probably just an opportunity. They recognize an opportunity there. And then about a third of my clients are, can you teach us about FMEA, or could you do this data analysis, or could you, do this specific task? And so they're very discrete little projects. And I'll go do stuff like that. The hardest ones are the ones that they shipped a product and half of them failed in 3 weeks, which is a true story for this one client I got. And they had enough money to try again, and they were able to launch again. They survived for about a year or so, but their brand identity was just gone. Wow. So they never recovered from that. And they made a very, very basic. So you remember Fitbit? I think they still sell Fitbits, right? There was a competitor to theirs, and they said, well, it's on your wrist, and you got to be able to use it anywhere and wear it in all day long. And you got to wash your hands, take a shower, go swimming. Should be all right. How do we test that? How would you test that? If you're creating a little wristband thing, what would you do to figure out if it survived in the water?
You jump in.
That's right. Well, they went one step further. They went to Switzerland standards for watches, because watches come with like water resistant, 50-foot dive watch, things like that. And so they found a 50-foot, I think it was a 50-meter resistance, and put it in that deep of water for 30 seconds, pulled it out, shook the water off, and it was still working. It's good. What they didn't notice is that a week later, all of those samples were dead, because it took about a week for the water to create the corrosion, which shorted it out. Wow. And killed it. The watch standard is if there's any water inside of it, it's a failure. But they had no way of opening their product to see if, because it was molded. but water still gets in. And so they miss that key element of corrosion takes time to occur. And that's what water causes most often with a product. And yeah, they shipped, I think, 70,000 units and 50,000 failed in 2 weeks.
Wow. I mean, talk about impact on the business. When you oversight reliability, I mean, that's huge.
It is, but you realize that there's time to market pressures. We got to get out to the holiday events. I've got 3 new inventions to do today. I got to set up a supply chain. I got to set up a manufacturing line. I got to set up advertising. There's a lot to do when launching a product. And reliability isn't immediately visible like all those other things are. You either know you got the right packaging in-house or not. You can see it, but you don't really know if you got a reliable design until it really gets to your customer. And there's things we can do to poke into that and understand it. But there's a lot going on, and it's just one more thing on the long, long list of things that we have to do. Unfortunately, if it's not designed and manufactured well and it fails, there's not a lot of recovery from that. And so unfortunately, those are the ones that I know I can help if they have the ability in the market to recover.
All right. Well, thanks for that, Fred. You talk a lot about mean time between failure. Tell us a little bit more about what that means to you, why it's important to track or not track.
Please never use MTBF, and I haven't opened up your product to see if that's central to it or not. But if it is, please change that. Do not make that the default. Mean time between failure is an average, right? It's the average time to failure for something, or if it's a recurring repaired system, it's the frequency of time between failures. The units itself, MTBF, is actually an inverse failure rate, right? It's not a duration. So if somebody says 50,000 hours MTBF, that does not mean it's going to survive for 5 years without failure. It's a very common misunderstanding of what that metric means. It's not a failure-free period, right? It's a 1 in 50,000 chance every hour that it would fail. That's what it means. Most people don't understand that. And then you bring in statistics to it and their eyes glaze over and you lose everybody. It's an average, right? Depending on what the actual time to failure distribution is, it could be, the average could be very, very short or very, very long, but it doesn't tell you what the spread is, what the standard deviation is. It's just a single number. It smooths out stuff, so it basically obscures the exact information you're looking for. Do I have an increasing failure rate or a decreasing failure rate? That's gone with MTBF. I could go on and on. I actually have a whole website devoted to it. It's called NoMTBF, NoMTBF.com. And I started this concept. I was doing a presentation at a conference and I was getting introduced, and somebody had just asked me a question about my supplier will only give me MTBF. No, it was I have a customer that wants me to give them an MTBF report. And he was like, what is that? Why would anybody want that thing? So I got on stage and I asked the audience, how many of you have run into people that are confused about what is MTBF? What does it really mean and how do you use it? Everybody and these are all reliability folks and quality folks, and they all raised their hand. So I threw away my presentation, and for the next hour and a half, we talked about MTBF and how many ways it can destroy your business, right? It just is exceedingly poor and misunderstood metric that unfortunately is used as a surrogate for reliability. And so it's, I write about it a lot because nobody else is saying, hey, don't use this. This is misleading. This is misunderstood. This is not the information that you actually want to get. That kind of thing.
Absolutely. And that's very interesting that you bring this point up. What we always talk about here at UpKeep is, it is really important to track metrics, to track a metric and aim to improve better than you were yesterday.
Yep.
So knowing, that MTBF might not be the best metric to track, what should we start tracking? What are good metrics to track as a maintenance reliability team?
For a maintenance team, it's uptime, right? Availability, but not the MTBF over MTBF plus MTTR. Those are averages that obscure what you're really looking for. If you have a 8-hour shift where you're running equipment, or you have a run that goes for a week or 6 weeks, your ops manager wants to know what's the probability that if we turn this equipment on and start the shift or start the run, that it'll complete it, right? How many hours of our schedule are we going to actually be producing products? What's our availability? In its true availability. And in today's factories, you can measure it directly, right? You don't have to estimate it or take samples or anything else. Oftentimes, that's the most important one. Now, of course, reliability and time to repair come into play in that. But I'm still interested. There's one factory I work with, they were canning soup, a big famous soup maker. And what a loud factory. They had tin cans all over the place. And one of the things they were interested in is and this was like a $10 million project of, do we add redundancy or not in order to improve our availability and our ability to quickly switch the line over from one product to another product. And what they found is that when they switched size of cans or size of bottles, for example, that they had a very, very high failure rate until they got it all tweaked in and tuned in and everything else. And they were working on their changeover methodology also. But they were looking at, if we can get to that lower failure rate quicker, this would make sense. We'll spend the $10 million and adjust our lines. If we can't do that, then it's not worth doing. And we'll work on other methods to improve our changeovers. And it was a decrease in failure rate, but the only metric they used was MTBF. And so if the run went for a week, you got a great MTBF. If the run only went for 6 hours, it was horrible. And that's not helping you. You need to see the pattern that's occurring. Every single shift showed this decreasing failure rate. And so we did a lot more modeling of that changing failure rate, and then found that sweet spot of how much, and it balanced with what their investment was in order to get those changeovers to an appropriate failure rate quicker. But if they ignored the changing failure rate or used a surrogate which masked that information, it would have taken them a much, much longer to find out what to do and how to move forward with it. So that's part and parcel of why I really don't like that metric.
Absolutely. Kind of pivoting a little bit, where do you see the future of reliability going? What are you excited by?
Yeah, nobody will be talking about MTBF anymore. That's one future I'd like to see. In the Speaking of Reliability podcast, we were talking about this morning. It's one of the things we're seeing is that more and more folks are not, and not just reliability people, but ops managers, design teams, equipment manufacturers, suppliers, everything else. They're spending less and less time truly understanding failures and failure mechanisms, right? Now, some are good. There's no doubt. There's still some organizations that really go all the way and fully understand things, but we're finding more and more people are not doing that. So when I bring a failed bolt into the shop and say, what could have caused this? There's kind of a blank stare. Well, and it's, did you replace it? As opposed to asking, was it the appropriately designed bolt? Are we using the right standard or the right hardness or the right diameter or whatever it is? Was this a defective bolt? Was there something wrong in the metal itself? Let's do the study of the metal. What kind of fracture was it? What can we learn from that? And you see it every now and then that people share their failure analysis and techniques for doing that kind of work. Yet I see that as declining. So in order for us to get better at what we're doing, more and more people have to become better versed. I think my English teacher is cringing at understanding failure mechanisms. How do things corrode? How do things deform? How do things overheat due to electrical current changes or resistance changes? Reliability gets involved with material science, electrical engineering, mechanics, all kinds of cool stuff, right? And even more so now with more and more robotic equipment, we get involved with software. So it's understanding how those things fail, either from a design decision that was poorly constructed or made, to material variation, to changes in the environment that change the stresses that are applied, all the way through to how does it manifest as a failure.
Mm-hmm.
And I see more and more need for that. And so that's one place I really hope things will go to. And it's not that we've never done it. We've got way better tools than we ever had to understand failures. So I think we can get better at it. Coupled with that is, with that understanding, then we can use this Internet of Things, right? We can use the sensors on the equipment. We can monitor vibration live and look for misalignments as they occur. All of those things are only possible if you understand the failure mechanisms. You know, somebody comes in and goes, oh, I'm going to do Internet of Things, and they put sensors all over their factory and they get terabytes of data, but there's no understanding there. They don't know what to do with that. So it has to come back to truly understanding how things fail. I mean, down to a theoretical level, then put your sensors in, then take proactive action to prevent failures. But I see there's going to be this dramatic need to do that level of understanding in the near future.
So what I'm hearing is it really starts with the understanding of why. Where do you go to learn? Where should others go and our listeners go to learn more about understanding failure mechanisms and the 30 million different ways a bolt can fail and why?
Yeah. 30,000,006, I think. It was last time I counted it. There's a lot of ways. It's a never-ending process, right? Start with the basics. Start with what's failing now, and go talk to your senior folks that understand how it works. Go talk to the chemists and the material scientists. That very first project I work on, I was in the chemistry lab half the time trying to understand this oxidation process and why it didn't go all the way through the material and just what was really happening. It's part of it. I think what makes a good reliability engineer is that you're just curious of how things fail. Now, the downside is it sometimes makes it difficult to get on an airplane, but especially when you see the cracks in the wings and the pilot says, oh, they're not that big yet. Like, okay, that kind of thing. But where do I go? I read, and I have a library. I go to Amazon is one place. It's a quirk, I guess, is I go to Amazon and I search for books on reliability engineering or reliability in general. And then I sort them by price, by the lowest price first. And there's a bunch of books, really classics, that are available for thousands of dollars, which I don't get. But there's a whole pile of them for under 5 cents or for 20 cents. And they make money on shipping, I guess. I don't know. It costs $1 to ship a book. And so I go get, 5 or 6 of those every month. And some of them are old and some of them are dated, but some of them have little gems and insights and so on it. Now, if I was really serious about learning about a particular failure mechanism, I go to the library, right? It's all online now. Go back to your alma mater and get library privileges. I teach at University of Maryland, and so I get faculty access to the library. And so I search and get the technical papers and the books and that are the state-of-the-art understanding of that mechanism, and then use that to design tests or to alter designs or suggest improvements. I'm probably doing that every month. Wow. I'd say is on some failure mechanism or another. But to get started there's some great textbooks out there that give you some of the basics, what is corrosion, what is drift, what is creep, those kinds of things. And then it's move on from that to what's relevant for your environment. And then just keep asking questions and keep looking. Library is your great resource, and just keep reading and asking and experimenting. Absolutely. So where I go is I talk to folks like you, and all right. On Ascendo Reliability, we have, I think, close to 20 authors that have been active at one point or another. So there's lots of literature from engineering management to detailed failure mechanisms. And then clients are a rich source of how things fail. So it never really ends.
For worse. Yeah.
That's right.
So what I'm hearing is like, it's all about just being curious. It's all about reading more. I could also see, this idea of going into the many, many different ways a bolt can fail, going down a very long path. How do you, any like tips, advice, recommendations on how to prioritize, different
That's a,
failure mechanisms?
yeah, that's a good question. It's, um, usually there's, I mean, for vast majority of materials and equipment and items we use, like a motor, right? Well, what's the basic technology of that motor? A quick Google search will probably find a dozen articles that say, here's the top 5 ways these can fail, right? Once you rule those out, then you can go start looking more deeply. But if those cover 95% of the failures you're ever going to see, right, it prioritizes pretty quickly.
Yep.
Once you know the basics of bolts, for example, tend to fail from shear or metal fatigue, right? They just get repeatedly loaded or bent and then relax, and that creates a brittle fracture, which appears completely different than a shear, right? Just a complete overforce of it. But that's vast majority of them occur from one of those 2 ways. And so by being able to recognize the pattern in the fracture surface gives you a pretty good clue what you're dealing with. And then you can go make some more measurements or do some more analysis of that structure to figure out what are you going to do about it. But electrolytic capacitors, right? They fail through dielectric breakthrough. The dielectric layer eventually erodes away, and they will all fail that way eventually. But if you don't manufacture it correctly, or it's not designed correctly, it'll fail because hydrogen builds up inside of it. And that's that little crosshatch on the top of electrolytic capacitors is so that they can vent. When this gas builds up, it's got to go somewhere. So they make it easy for it to go in one direction. Unfortunately, it's really corrosive and it kills everything else around it. But understanding just fundamentals of any device, any component, any fastener of how they can fail is the starting point. So and that's just basic knowledge, I think, not just for reliability engineers, but anybody dealing in the reliability and maintenance world.
Absolutely. Fred, you are a wealth of knowledge. Where can our listeners find more ways to connect with you, read more of your materials, articles, and learn more about, you and what you're doing?
Okay. Well, I mentioned accendoreliability.com, and it's a platform for folks like you to, share your podcast and get the word out to an audience. It continues to grow. We're bigger than any professional society now in attendance and engagement. And I heard it at a conference a couple of years ago that in 1 month, Accendo Reliability puts out more content, practical, useful content, than all of the professional societies that deal with reliability work combined in a year.
Wow.
But that sounds pretty amazing. So I went and added it up. And counting the conference papers, we do that every month. Right? We just crank, there's a lot of contributors that are willing to share their information. So Accendo Reliability is the platform I'm building with the help of a lot of other people providing content, and a lot of my content's there too. Obviously I'm up on LinkedIn and more than happy to connect, and that's where I share a lot of the new materials that comes out and other people's work and my own work, answer questions every day for people. That's where I get ideas for articles and keeps me in touch with the industry. And knowmtbf.com, talked about that if you're really interested in diving into that. And let's see, reliability.fm. It's a website for a podcast network. And so it's a number of different ways to find my about page and contact info.
All right. You heard it from Fred. Awesome. Thank you so much again, Fred, for joining us.
Hey, very welcome, Ryan. It's my pleasure.
Absolutely. And thank you to our listeners for tuning in to today's Masterminds in Maintenance. It was a great chat.